Let's now try to solve this problem from weekly contest 295, 228 steps to make array non-decreasing. Please help to press the like button if you like it, of course. Let's start with the problems. Then we talk about tactics. We talk about code implementation and time complexity. Start with the problem. So we have index array nums, which is a zero index array, where one step of operations that they gave us is to remove all elements at index I if the index before it has the value greater than the index I itself. Okay, then we need to return the number of steps that we can perform until nums become a non-decreasing array. It means until we cannot do these operations anymore. That's another way of saying it, because when your value before it greater, that's what violates the non-decreasing terms, because it means it's decreasing, right? It means that if it is equal, that's actually fulfilling the values of non-decreasing. Now an example of this. Given this array, the return is there are three steps to actually make this into non-decreasing. So in the first step, we can see that we will remove 3. Then because 5 is greater than 3, we will remove 3 here because 7 is greater than 3, 8 here because 11 is greater than 8, and 5 here because 8 is greater than 5. Okay, notice that in the first step we don't remove 4, because when we evaluate the first step we don't remove 3 right away. That's one thing to be noticed. The 3 is still there. That's why in the first step number 4 is not removed. Okay, and then step 2, in the step 2 is the same step, basically 4 removed because 5 is greater than 4 and so forth. And at the end we resulted, after the step 3 we resulted in with non-decreasing array where we cannot do it anymore. Therefore we return 3. While this one, because everything is already non-decreasing, the return is 0. Now how to do this? Actually, now we talk about tactic. A brute force one definitely to just translate this into a code where we create the function, for example, to do the steps, and then we run the steps until the steps not decreasing, not removing anything, right? That's one way to become a termination criteria. So if we do that, we actually will not be able to be accepted because it will be too slow for this problem. It will reach a time limit problem. So what can we do to actually make it quicker here? Okay, so if you notice one thing, the way we can do about it is, once we the way to do this is, notice that if we separate this into multiple non-decreasing groups, then we know that for that non-decreasing groups, we can actually jump towards the most of what we can remove. Let's see what I mean. So let's take these examples. Maybe rather than taking this example, let's use a artificial one first to actually deliver the points that I mean. Let's say we have this, okay, and then we have what after 5. Let's make 6 and 6. Let's make a 1 2 3 again. Okay, so if you notice here, I have 3 range of things if we try to separate this into multiple existing non-decreasing array. Okay, so what is the things that we can leverage from here? Notice that we can make a jump on the steps we do, but equivalently still correct by looking after separating this into three different existing non-decreasing array. Because what this means is if we do the step 2 times, right? Not 2 times. In this case, 3 times. We know that we can do it simply by removing all these 3. Why 3? Because notice that this group of array actually have all its elements lesser than 10. Meaning that we can, if we do 5 steps with only these 2, we actually equivalently removing everything. Why? Because these all are actually non-decreasing already. So all the element with the neighbor here with its steps from 1 to 5 will not actually make any difference. The difference always comes when the number is neighboring with the 10, because the 10 will be the one that is violating the non-decreasing. For example, step 1, it means we remove 1. But do we remove 2 in step 1? Of course not, because these are already non-decreasing. Okay, then step 2, 10, we remove 2 because now 2 become the neighbor of 10 and violating the non-decreasing terms. Then we remove 2. So all that step we can simplify by simply noticing that all these are actually lesser than 10. So 5 steps forward can be directly do without running the steps in particular, but directly by doing this. Okay, but why we choose 3 rather than 5? Because it is true that this relationship with the neighbor before it is 5. But how about this? This has a relationship with the neighbor before it that the largest value is 5. So the same logic can be done only 3 times, 3 steps. That's what is guaranteed with the current compositions, okay? The current arrangement. So if we have 5 and 3, of course we chose to jump with the smallest possible, because 5 is not possible for this. This only have 3. Why do we need to be careful about that? Because that's what is guaranteed. The smallest group of jump is the one that is guaranteed that everything will be fine. Okay, so what happened here is in the first step we do that 3 jump and we know we calculate this is the first group, so there is nothing of course to be care about that part, because the rule is about comparing it with the one before it and it doesn't have anything before it. While this one we know that we have, compared to the one before it, the number 10, all 5 are lesser than it, so we can jump 5 times. While the final part we jump 3. Out of this the mean is 3. Direct jump of 3 is guaranteed to be okay. So if we do direct jump of 3, what it means is now this one become 1, 2, 3. So become 4, 5. We eliminate the 3. That's what it means jump by 3. And the final part will become empty array. Okay, so after doing this, we do another session similar like this one, but actually we can check also whether there is anything that actually now we can merge. we can merge into non-decreasing group, but there is nothing because this is actually 10 is still bigger than 4. Then at this point we update the values because we already jump for 3. Now this become only possible for jump of 2, and actually because this is 0, another way to look at it, we can actually eliminate this. We can eliminate all the empty. So the next step is actually to compacting the group of array. We remove this because now this one is already having no membership, so it doesn't matter anymore. Now after that we do the calculation of how many jump we can. Then from this on we know that the minimum is 2, right? The minimum is 2. Okay, so after we got the minimum is 2, now we do the same thing and jump into 2. That's it. Okay, and after this we know that there is nothing else, it's only 10. It's already become one non-decreasing array after we remove what is empty. Once we already got only 1, it means it's guaranteed that everything is non-decreasing, and this is the answer. And during this, how do we calculate the step count, right? Of course, the step from here was 0. When we do the first grouping, this is actually what you call it, possible. One of the way to do this, there's we can, this is still 0 because we don't remove anything in this case, but actually we can already start removing 1, because the way we group this, if you notice, is when we detect there is a violation. So this separation happens when we detect 10 and 1. So another way you can do and to save something in between is actually to directly eliminate the place where you detect. Okay, if you do this, then the step become 1 after the separation. So that's a different flavor. More or less it's the same, it's just a little bit of optimization, not optimization, doing things at the same time. So but in this case, remember that this calculation become 4 and 2 and the mean was 2. Okay, and then after we do this, what happened with the step is actually the step become 1 plus 2. Why 2? Because we choose to jump 2 times, right? 1 is from before, 2 is from the choices in the next iteration here. Actually, let's don't calculate it here. Calculate it after we do the removals. So after this step, we know that when we do this step, that is equivalent with doing the step 2 at a time. Okay. Then after that, we do the same thing. We calculate. Then it means another removals of 2. This means it add another 2. And at this point, there is nothing being changes. The step doesn't change. Then we return the step, which is 5 step. Okay, so that is the tactic basically. We will start by separating it into non-decreasing group. After separating it into non-decreasing group, we calculate how much we can direct jump. Then use the minimum at that set. Then we jump. After that, we update our step based on how much we jump. Then we do another session where we either actually removing the empty array or we merging the things. In this case, we don't have a case where we merge the thing. So let's make that clear by having a little bit differences of examples. So rather than 10, we do 3. Okay, this will help us. The first, of course, still the same step was 0. Then it was step 1 when we do the separations. We know a little bit though that it will be this and also this the same. But this calculation is a little bit different because now 3 is only capable to reach this one, okay? Only one, which is 2. While this one, maybe let's make it 4. So it's jumping more than 1. So in this case, this will be 2. This one stays 2 because 5 and the other. The minimum out of this, of course, 2. Then what happened here? What happened in the next step is we do the jump. It means we remove this and we remove this. Then we need to do some we update the step, which is we do 2 step. Then we do the compacting the groups. Okay, compacting the groups here means that we remove what is empty. Okay, we remove what is empty, and then we also see whether there is group that is neighboring that become non-decreasing already, which is this one. You see 4 and 4. The last members of this is a non-decreasing pairs with the first member of this. It means we can merge this. Okay, then we check whether now we only have one group, which is true. At this step, we return the step. Okay, so this is actually the thing that I want to point out by changing the value 10 in the previous example into 4. So that's about the tactic. Okay, remember what was it about? Separations, calculation how much we can jump, do the jump, update the steps, do the merge and removal, tidying up what after we do the jump, we tidy it up into a group of non-decreasing array and group of array that still have members. Then we check whether it is only left one. If it is only left one, we don't need to do anything. We can just return the step. Otherwise, we do another iterations of this. Okay. Now that we have this, let's translate it in the code. See that the efficiency here comes when we do a jump, multi-jump at one step. So rather than doing the step as it is, we find out that we can do the jump. That's how we can make this with algorithm that is much faster than doing the steps there, just as it is. And I've prepared this code. This is the one that I submitted. So once again, the first step was to do separations. This is a prepared variable to hold the groups. Let me close this down because we don't need to hide this anymore. We can see the code now. The groups is basically what holding this. Okay, that's what groups. GI is just an index in the group. GI later on is just to count the index so that we know what to be at. Step count is what is step here basically. So the first part is to do this, okay, to separate it into different non-decreasing group of arrays. So basically how to do that is we explore its number. We need the index and the value because later on we will do this check, right? This is the one that we do the check for the non-decreasing. That's why we need the index. So if the index is 0, it means it doesn't have a previous member. we directly just do an addition to the existing group's GI, which is of course starting with index with the group 0. Otherwise, if it is not index 0, if it index 1 to the end, we need to check whether it is having non-decreasing relationship. If it is violating. If it is having non-decreasing, of course we just add it to the current GI position. Otherwise, if it is violating the non-decreasing, what we need to do is, if it is this is an efficiency, basically. Let's talk about this part later. What is important is actually this part, where if the group before is actually having a member, which means if this one have something filled already, it means this is the time when we create another array. Okay, that's what it means. And then we position our index to actually fill in that index. So notice that we need to do this check because we want to make sure that we don't leave something empty. What is an example when things can get empty? Things can get empty when we have consecutive numbers of non-decreasing violations. For example, 10, 1. If we change this into 3, and then this is into 1, okay, then this is become 4. What happened is when we separate, we got 10. Then because we know that this is if we follow this code, 10 was inserted, but 3 is the position where we detect this violation, and we know the length group is 0. It means we're now preparing the empty, right? And then the GI, pointing here. Okay, then what happened next is, in the next iteration, we are looking at number 1, and where number 1 here is actually also violating, but this one is empty. If we don't do this check, what it means, we will create another disk, which is not good. But actually, because later on we need to take care about two separations, so that's why we need to detect if the previous one's still empty, and that happens when this is the case. When that's the case, we don't need to do these things. Then what happened next is we do another iteration. We go to 4, and 4 is not violating. It means it goes here. Then we can just append 4 here. Okay, so that's why we do this check. And what is this? This was something that I do because I realized that what really important for each of this, if you notice, is that we're comparing the last element with the first in the next element. Okay, that's why it is so simple to say that if we the GI0 will only always need just the last element for our purpose to count the step. Okay, so for example, if we have, rather than 10 here, we have 1 to 10, actually this become 1 to 10. And it doesn't matter what is this 1 to, because we don't have any member in previous one, so we can save some space storage there by making this equivalent with this for our purpose of steps. So this is not that much important. This is just a small storage efficiency, but that's about it. So this is the separation step. Okay, now once we finish with the separation step, this is what we do. If the learn groups is already 1, this is our termination criteria, if you remember, then that's it. We return the things. But if after the separation we only have 1, it means there is nothing that we remove actually. That's why we return 0 directly. Otherwise, you can also do return step count, because step count is still 0 here. Then this one, what is this? So this one is when it is greater than 1, and then the final part, this is basically checking if the last part was empty. for example like this. Then we want to remove it. So this is the place, this is one of the steps when we try to compacting the things, okay, making it removing the stuff. Then if the learn groups after the removal stays at 1, it means we already have the things, but the difference here, we return 1. Why? Because when we have more than 1 in the first place, although the last one is an empty things, it means there was a removal happening during this process. That's why we return 1 already. And at most, of course, it's only 1, because at this separation, we actually only remove 1. And then this is the step when we do the count up and so forth. Let me copy this. Okay. So just now we already did this, so I will remove this part. Now step count is starting from 1 because after the separation and it still have more than 1 membership, it means we already remove 1. Remember that, right? Now this is the one where we min SC is basically what min here, and GC is basically these values. Okay. The first one I just put it as 0, just that because we never really going to use the value here anyway. Then we count up the GC. How to do that? Basically, this is the step when we do these things. For each member, each group, first we grab the one from the previous. That's why we start from 1, because 0 doesn't have previous. We got the largest one from the previous index. Okay, and then we want to calculate the GC here. So first, for this problem, for example, we calculate this one, what we want to find this for. So what happened is, for the range of j in 0 to the value, basically this is iterating this, okay, to j is the index inside this. If the previous largest, which is in this case 10, is less than the group, that's when we find out the number. In this case, it will comes up nothing actually less than equal, right? Everything will be 10 is greater than any of this, so we'll never go here in this case. And then this is where we check, that is the edge case where we check. If this GC is still none, it means that everything in this group was lesser than the previous largest. This is where this GC means the total equal to the total length of this, okay, in this case 4. Let's take an example here where we don't have that, just to bring out the point. So if we took this one, when the 10 is replaced with 4, what happened here is when it is exploring this, we notice that this condition met when 4 meet with 4. At that point, we know that the j is 0, 1, 2. The j is 2. So that's how this one can go, okay? So now let's continue. After that, we append the value of this GC. So basically this 4. GC is this one once again. So now it becomes 4. Then if GCI is greater than 0, which it is, this is where I'm trying to do what was the minimum. This is where we compare the minimum. It will compare the minimum of the existing or GC1. But of course, if it is starting with none, we just fill in the GCI directly. Okay? And then it will iterate again, and the next iteration is about this, which resulted in 2, and the mean become 2. That's what this is about, basically doing this step. Okay, and then when min sc is still none, if in case min sc is still none, means this one never goes in, right? If this one never goes in, it means there is nothing minimum there. It's zero. It means that everything is already non-decreasing. If it is the case, what is an example of it? Maybe let me try to create some example that doing that. If this is 6, 7, and this is actually 1. What is the original problem possible for this? 1, 2, 3, 4, 5, 6, 7. This one is 4. This one is 1, 2. Maybe this one should not be 1. This one 2, and this one is 1. So if this is the original problem, we know that this is where it violates this one, because 2 is greater than 1. Another violation is in the 4, but after that we actually already have a non-decreasing array. So min sc here, there is no min sc because GCI will all 0 here. Okay, because everything directly, when we do the check at this part, 2, 2, that is j is 0. That's it. 5, 6, j is 0. That's it. So min sc will stay none. This is an example of it. And then well, actually this one not needed because step count is already calculated there. What happened then is actually we do the compaction. Compaction is this step when after we do the jump, well, not yet. This is the part where we do the compaction, means we do the cut. After we calculate how much we can cut, we do the cut, okay? That's what it is. Let's bring this down. So now we are talking about how we do this step. So step count plus equal to the mean. Basically we are doing this. Okay, we are updating the step count. That's what is this. Then this one is preparing for the next group, because we're going to modify the membership of it, and also the next min sc. This is actually doing the whole calculation again. So this is why there is a while loop here that is actually waiting until the group left only with 1. This is where we stop because we already have the step we need. And what happened here is for each of the group, it will check for it will do the minimization, which is doing the jump. So from the last bin sc, if you notice, this is what it do. It cut the group into from the minimum it has to the last, and it start from the group 1 to the next, of course. That's why we took min sc or GCI. Okay, because it could be that some of this actually doesn't need to be removed at all. For example, if this lesser than 5, this is 6, 7. This is actually 0, but the mean is still 4 because we don't include 0. 0 is means we don't need to do anything about it. Okay, so the non-zero GCI minimum, that's what min here actually means. Let's revert this back. So that's a part of it. Then if the learn group is greater than 0, it means there is still membership here. For example, like this one, after we jump 2 times, it still have members, right? And then what we do is we check whether this is still whether this become a non-decreasing part of this remember the example just now. If this is 4 and 4, that's what it detects, this line detecting this. If that is the case, what happens is we actually going to that's why we need the other what you call it, placeholder here, because this is where we do the merge and removal of the empty. When this is happening, the next group will actually this is the next group before. Then when we go to the 4 5, rather than creating another entry in the next group, we extend. That's what happened. Okay, but if it is what you call that, if it is not non-decreasing already, like this one, if this is the resulting things, then what happened is in the next group it become another entry. What we do here is actually we also do the GCI calculation. Okay, the next GCI will be minus it. So if you notice this one, so this is the part where we calculate this one is calculated by 4 minus 2. Okay, of course we cannot go to negative. If we go to negative, we go to 0. It means there is nothing we can cut. And then while the learn groups I is still greater than the GCI, GCI here means that the GC that we calculated, and then next group minus 1, this is the one previous, the last member of the previous one is greater than the group values, then we increase the GCI by 1. Okay, so that is the case here. What it means is actually, if now, because it's not always that easy like this one, where we directly have the GCI just like that. For example, when this was for, what was it, 4 5, if we change this, for example, into this problem for me to deliver that one. Okay, so the initial one, we actually going to be able to remove this momentum. 5 means 0 1 2 3 3, and then this one is actually still true, 2 mean 2, so the next one will actually make this into 5, and then remove 2 become 4 and 5, and this one become empty, right? Now notice that how do we calculate GC? 3 minus 2 become 1. Right. Actually, we might not really need this one, because what this is actually trying to do is actually this one is trying to make sure the GCI up to the game. It means that if the next groups actually increase still greater than what it was before. Oh yeah, right. Possibilities here is if actually we have this, for example. Okay, if we have this, This is actually what it is trying to take care about. So what happened here is if the previous one become a new previous, that's what this one trying to handle. Now I remember this edge case. So for example, this one 5, and then this become 2, right? Because every 5 is greater than everything. Well, for this one it only become 1, because that's the thing. And finally this one become 2, and from this the mean is actually 1. When the mean is 1, maybe just do this 3 so that we are faster in our examples. This one become 1, this one become 1. Why 1? Because 3, 3. So that's index 1, right? So the mean become 1. If the mean become 1, then the next iteration we will have this empty. And then after this empty, we will have this one, this, and this one come this. Okay, and notice that when we do the next n, it will start from having all the 5. This is the next group. This is all the 5. Then after that, when we calculate this, we actually know that the group is not greater than 0, so we don't add anything into the next group. Then when we calculate this, we see this, we calculate this, this is where we go. Okay, so when we go here, we know that the new GC by the normal calculations here, actually this one of course become 0, this one become 0 also, because we choose the 1, this one become 1. Now notice that this becomes 0, but its next friend is actually 5. Okay, its next friend is actually 5. So that's why the GC0 is not really correct. That's why we have to do this one, where it checks that if these things have members, which is it has, and then the group members numbers of course still greater than what is the new GC we have, which is 0, 3 greater than 0, it means there is a possibility that GC is not 0. Basically that's what it says. Then we check, then the next group minus 1, which is this. Okay, this is the latest in the next group, and the final member of it is 5. Then we do the comparison to get the GC. When does it if it's still violating, we increasing it. 5 greater than GCI here, which is 0, right? 5 greater than 3, then we increase the GC. 5 greater than 4, index 1 is 4. Yes, it is increasing the GC. 5 is not greater than 5, and that's it. So this is basically the case that this is trying to handle. So the case when this become empty, and the next one actually now having the previous of this, which is this. Okay, so that's what it is. Then after doing all that, we can add the next GC, which is what? This is next group, next GC. This is what makes the next GC become the 2. Remember, we skipped this one because this one was empty. That's why it won't go here. And then next MNC is the same logic. GC if next MNC is none. Otherwise, we do the minimum from the next MNC. And then next group, appending this. That's what it's doing. Okay, so notice how we eliminate the empty by having this, how we actually joining the things that is what you call it, non-decreasing by having this, how we actually handle the rest by doing this. Then this is the unique part, its case, where actually the previous one become an empty stuff. That's why we do the check in the next group rather than the group itself. And then we increasing the GCI based on a new evaluation from the new previous neighbor. Then after that, of course, we now update the group min SC and GC with the next one that we calculated here. At the end of it, when the group length is become 1, that's when we return the step count. So that's the code implementation. To be honest, this is this week hardest medium problem. Okay, because to get the idea itself is actually taking some time after looking several kinds of possible problems. That's where the idea come into, and then translating itself is not that easy. Okay, even translating the idea itself is not that easy. So that's about it. We can test this one. It is accepted. Okay, so how about the time complexity? This one, the separation is enumerating. Every enumeration we do either append or we do comparison, append, and so forth. So this is actually big O n, where n is the length of the nums, not this n. Okay, length is the length of the nums. This one just big O1, big O1, big O1. This one is we doing it per group. Of course, the worst case is big O(n) if every group only have one member. Inside of this, let's see, there is another for J here, where the worst is of course if we only have one group. So notice though the correlation relationship between here and here, it doesn't mean n squared, because when we have an increment here, we have a decrement here. So in total, all this will still just do a loop of n, where n is the number of the membership. Because when what is the easiest ways to think of this, when this become the maximum, when it means a group consists of one member, it is big O(n). But when that happen, it means that a group only has one member. This become 1. You see that? That's why we don't make this n squared, but n. And the reverse is true. If this become n, which means a group consisting all of the initial numbers, length of nums, it means that this one become 1. You see that relationship? That's why although this is a 2-level for loop, actually this only costs us big O(n). So careful about that time complexity quirk. The rest of this is just comparison, appending, comparison, those are big O(n). So in the end, this part will be also big O(n). This is also only big O(n). Then this one, while learn group is greater than 0, this is a multiple iterations. Of course, this is also big O(n), because the worst is when we have n groups, when every group is consisting of 1 numbers, right? And then this is just increment, initialization. This is a for loop. While I in range 1 to groups, this is the same big O(n), if you notice, because this is actually the worst is when every group is consisting of a single number, and this is another loop inside the group. And then, but remember that this and this doesn't have the same correlation with the above. That's why I keep this n. And at this point, actually, this become, because this is inner loop of this become n squared. Okay. Then this one is just a, what do you call it? A copy of slicing, not copy, actually this is just slicing. And then this one is learn group greater than 0, just comparison, extending. And then this is just a mean comparison. This is a looping of the members. So notice that this looks like it could be n, right? But remember that it has inverse relationship with this. This become n when a group consists of 1. If a group consists of 1, of course this become 1. The reverse is true. If this want to become n when we do the extend and we do the while loop here becomes n, that's when the group consists, we only have one group with n element. That's why although this looks like it can make another big O n and this become big O n squared, it not. Because of that relationship, inverse relationship. That's why in total, although there is a while loop here and there is an extend here, this stays big O n. Okay? The rest is just appending and comparison. So in the end, this stay big O n squared because this one stays as big O n. This is just a reverse. That's it. Now if we see the sequences, big O n squared, big O n. So the largest, and the previous one big O n. So the largest is big O n squared. That's it. That's the time complexity of this solution. And that's about it for today. This is one of the trickiest part for this weekly contest. Thank you for watching. Hopefully that helps. Bye.